Okay, so I would like first to thank Doro for this invitation. It's a real pleasure for me to be back again this year with this presentation entitled GPC-based Therapies, so GPC for a group phenotypic composition. Okay, so let's start by recalling the ecological and evolutionary rationale, which is behind what I'm going to present now. Unfortunately, Drew is not there. So in the living world, as you know, many animal species live in colonies where the mobility of individuals is sometimes limited or even absent. This is the case, for instance, with corals, with tunicate, with bacteria in biofilm. And it has been demonstrated by ecologists that the success of these colonies, of this ecological lifestyle, is due to the task repartition between individuals, the division of labors associated with collective emergent benefit. And to help us to understand these interactions, evolutionary biologists have introduced the concept of group phenotypic composition, or GPC, that refers to the distribution and combination of individual phenotype within a group and how this configuration influences the collective behavior and the performance. For instance, it is known that the global properties of this shoal of fish are due to the addition of the individual characteristics of each fish together with synergetic effect, to be short. And it is also demonstrated that on the long term, the global property of this shoal of fish will influence the evolutionary trajectory of every member belonging to that group. So functioning via a GPC is clearly a strength, but it is also an Achilles heel, a structural weakness. Why? Just because functional coordination creates systemic interdependence. And when there are some alterations in the GPC, whatever the reason, the critical loss of the GPC integrity can sometimes reach a tipping point above which there is a collapse of the collective systems. And there are many examples like that in the living world at the level of animal colonies, but also ecosystems. So we accumulate some alterations into the GPCs, and sooner or later we meet a tipping point and there is a collapse of the system. And just one example, in termites, for instance, it has been demonstrated that if you just alter the ratio between soldier and worker, you can induce a collapse of the colony. Okay, so that's very interesting, but what is in fact the relationship with a cancer? Tumors are also a group of cells that are living together, and there is a GPC in tumors. This is at least what we have suggested in this paper that we published recently in eLife. There is a GPC in tumors because there is a spatio-functional distribution of the intratumoral heterogeneity, and this can be described according to at least 3 dimensions. First, who is there? This is the compositional dimension. Then, where are they? This is the spatial dimension, and this brings us to the third point. What do they do together? What are the functional dimension, and what are the emergent collective properties such as the angiogenesis, the invasiveness, and the resilience? Together, these dimensions define the functional phenotype of a tumor as a group, the GPC of tumors. So the GPC of tumor looks like a theoretical construct, but in fact it is much more than that. It is a reality that is increasingly closely described through high-dimensional data sets that are generated by spatial transcriptomics, by proteomics, by metabolomics, by multiplex imaging, and by microenvironmental modeling. Then, in this paper, we have suggested that the tumors that are able to grow are those that have the right GPC at the right time given the microenvironment, which is far from being guaranteed in advance because, as you know, there is no predefined program to build a fully functional tumor. Thus, there are random proliferation of cells, Darwinian interactions between cells, and this produce all the time in a dynamic manner. This is very important, in a dynamic manner, various GPCs with various values. So probably most of the time, these GPCs are not necessarily suitable for the growth of the tumor. In that case, the tumor can remain stable, maybe for years. We can even consider the possibility that certain GPCs has a negative value. In that case, we will assist to spontaneous regression of the tumor, and sometimes by chance or because of bad luck, should I say, if we adopt the perspective of the patient, the GPC has a positive value. It is functionally advantageous for the growth of the tumor, and in that case, we will assist to the progression of the tumor. Okay, it's time to open a parenthesis just to highlight that reinterpreting the host-tumor relationship through the GPC shifts our understanding of cancer from a cellular disease to a conflict between competing functional systems. Tumors have a GPC, we have just mentioned that, but the host as well as a GPC. Multicellular organisms function thanks to an internal GPC, a spatio-functional architecture that emerged from the coordination of the constituent cells. And your health strongly depends on the integrity of that GPC. In this context, we can reinterpret the host-tumor interaction as a functional competition between GPCs, a conflict between two incompatible GPCs, the one of the host, which is an evolved one, the results of millions of years of evolution favoring the coordination, the adaptability, and the systemic stability, and the one of the tumor, an emergent one that evolves de novo in each generation under selective pressure for local persistence and rapid extension. While the pathological consequences of cancer are, as you know, very diverse, in fact, they can all be interpreted as the result of the progressive destabilization of the host GPC by the tumoral GPC, eventually leading to the systemic collapse of the host GPC beyond a tipping point, and this is the death of the host due to cancer. So it means that from a therapeutic point of view, we should of course target the GPC of the tumor to bring it toward the tipping point, but we should also reinforce and restore the host GPC to preserve internal coherence and to resist a collapse. So it means that from a therapeutic point of view, we should redefine the success not only through the tumor shrinkage, but also through the restoration of a coherent and a functional host GPC, suggesting that in addition to treatment that target the tumor, we should also favor interventions that support tissue repair, immune coordination, neuroendocrine balance, and systemic integrity, because this can help to delay or to prevent the collapse. It also suggests that we should, of course, favor host GPC-friendly therapies. It seems obvious, but as you know, it was not always the case in the past, and many patients died not because of the cancer, but because of the treatment, because very often the damage inflicted by the treatment has largely contributed to the systemic failure beyond the cancer itself. From a preventive point of view, we should also try to preserve or restore the host internal climate, a concept that has been introduced by Aurora and Doru, in a way that is not compatible with the tumor coherence. And it also suggests that we should develop some vaccines that do not necessarily target malignant cells when they emerge, but malignancies when they attempt to organize with an oncogenic GPC. So I close the parentheses and come back to the main talk. So this is an illustration of what could be a traditional cancer treatment. As you know, we target directly or indirectly malignant cells, and we try to kill the maximum of them. And in fact, it's not really surprising with such kind of approach that do not necessarily target the interacting components that are responsible of the functional network of the tumor. It's not really surprising that the tumor quite often can restore an oncogenic GPC or select for a resistant one. So we would like to suggest another approach that we call GPC-based therapies, that we could define as therapy that does not try to eradicate the maximum of cancer cells, but to induce a destabilization in the spatio-functional distribution of the intratumoral heterogeneity, so that the tumor is likely to switch from a GPC-A to a GPC-B, with the possibility to reach a tipping point above which the tumor is likely to collapse or to shift its trajectory. Let's consider a metaphor to explain that. This is a tumor with an oncogenic GPC. We apply a GPC-based therapy to induce a destabilization into the tumor. I agree that if the destabilization is not strong enough to reach the tipping point, the tumor is likely to restore an oncogenic GPC. But we are betting that this won't be the case if we are able to cross the tipping point above which the tumor is likely to adopt a non-functional GPC and to collapse, especially if there are also some alley effect, we'll come back on that just after, or to switch its trajectory for something that would be less problematic for the patient. So the good news is that I have recently obtained a big grant from the CNRS to explore this research direction. The bad news is that I'm still waiting for the money since months now. But if the money finally comes, we will develop this project through 4 work packages. One will be based on tumoral hydra, another one on ovarian cancer organoids, a third one will consider murine melanoma, and then we will do some mathematical modeling. So why this choice? First, hydra, as we will see just after, is a very interesting model system for the proof of concept. The tumoroid models, as you know, it's a very interesting tool to evaluate the efficiency of different therapies in control conditions. So why not GPC-based therapy? We need, of course, an in vivo validation for that, and we need also to develop a predictive framework. So with this approach, the idea is to induce different kind of destabilization using different means into the tumor, then to monitor the outcome of these destabilizations, whether, for instance, the tumor is eliminated or whether the tumor persists, but maybe without killing the host, and then to closely characterize using omics the different tipping points that we could reach with this approach. So let's see now first preliminary but very encouraging results with the hydra model system. So I said before, hydra is very interesting for the proof of concept. It's a small cnidarian species that develop tumors as demonstrated by Thomas Bosch in this Nature Communication paper a few years ago. It is possible to induce some destabilization into the tumor, and I have them in my lab. So recently we performed, for instance, total destabilization of the tumor. We used these protocols. In fact, we are able to separate all the cells that are inside the tumor and to put them back randomly. In that case, you will admit that the GPC of the tumor is completely changed. And what is crazy with that model system is that the cells are able to reaggregate to produce a new hydra, a kind of resurrected hydra, if you prefer. And we did that recently on 50 healthy hydra and 50 tumoral hydra. We have been able to obtain 27 resurrected hydra in the group of healthy hydra and 24 in the group of tumoral hydra. And today, that is to say 2 months after, 100% of the hydra are healthy, suggested that indeed when you induce a total destabilization of the GPC of the tumor, you can cure the host. But this is, of course, for the proof of concept. It's more complicated to do that on humans. As an example of partial destabilization, I will present some preliminary results obtained by my PhD student, Clara Asselin. So to induce some partial destabilization, Clara decided to introduce tumoral tissue into the tumor. She introduced healthy tissue inside the tumor. She did exactly the same without grafting any tissue. She made a small incision in the hydra, and she made also a camembert cut. And with these protocols, she was able to obtain 3 different scenarios. So the first one, in 12 cases out of 25, we observe a short-term recovery. That is to say that just after the GPC-based treatment, the hydra was apparently cured, but unfortunately for the hydra, the tumor came back. In 10 cases out of 25, we obtained a long-term recovery. And in only 3 cases out of 25, there was no recovery of the hydra. But what is interesting is the survival in the different group of hydra. The group without treatment, you can see that the survival is reduced compared with hydra with a GPC-based treatment. And this is exactly what we expected. That is to say, the alteration of the tumoral GPC improve the host survival, whether or not it eliminates the tumor. Another interesting result with hydra is when you alter the bacterial part of the GPC, of the tumoral GPC, using, for instance, antibiotics. When you apply antibiotics on tumoral hydra, you can indeed cure them. And this has been demonstrated by Raj and colleagues in this PLOS pathogen paper. And we have exactly the same results at the moment in my lab. So while we were waiting for the money to come, we decided with the different participants to the project to conduct a brainstorming to move forward on GPC-based therapy. And by revisiting the literature, we arrived to the conclusion that several successes in cancer treatment may sometimes unknowingly have resulted from GPC-based therapeutic effect. And this is what I'm going to present now. And this also corresponds to a paper that is currently in revision in a Nature Partner journal entitled Precision Oncology. So as you know, modern oncology remains dominated by the maximum tolerated dose paradigm that is grounded in the assumption that reducing the total number of cancer cells correlate directly with disease control. But as you know as well, with this logic, there are some paradoxical outcomes, because sometimes with very aggressive treatments that are able to push the tumor below detectable levels, we have some relapse, while conversely, sometimes with modest or intermittent interventions, some tumors, not all of them, but some tumors remain stable or even regress. There are a lot of papers showing that. I'm sure that you know some of them. So that clearly the therapeutic success is not always explained by cancer cell killing alone. So we have suggested that the situations that achieve disease control without necessarily eliminating all the cells could potentially be understood as form of GPC-based therapies. So among existing therapies, it is already known that several therapeutic strategies are known to induce some destabilization in tumors, but clearly they are much less integrative than what we are suggesting with the GPC-based therapy, and it is also possible to reinterpret them through the lens of GPC-based therapy. And maybe the main novelty, the main originality we are bringing with the GPC-based therapy is to provide an unifying conceptual framework that can explain why, how, and when it is possible to destabilize the tumor, and what sometimes it works to guide the optimization and potentially to inspire new therapies that would rely on that principles. So let's consider the therapy as a way to modulate the GPC. That is to say that the first objective is not the elimination of the tumor, but its systemic reconfiguration. So from that perspective, in fact, any kind of intervention could be potentially reframed as an attempt to reshape the tumor GPC landscape. In that case, the success is not evaluated through the tumor mass reduction, but through the loss of internal functional coherence. And it is important to distinguish between the destabilization that could be considered as superficial, that is to say they cannot prevent the tumor to reorganize and to relapse, from those that can be considered as efficient, that is to say that can lead to a durable control or collapse of the tumor. Even if the first objective is not the eradication of the tumor, this can be, of course, an outcome for sure, especially if the destabilization is very high, and also if there are some Ali threshold, Ali effect. So I'm not sure that everybody knows what are Ali effects. So in simple terms, and applied to tumor, Ali effect describes a situation where a tumor cannot grow or even survive when it becomes too small, because cancer cells depend on each other to function effectively. So if you are above the threshold, the tumor is likely to grow, but if you are below the threshold, the tumor is likely to go extinct. So why does this happen in cancer? Just because cancer cells are not independent, and at low numbers, they lose essential collective advantages, typically the angiogenesis, the immune evasion, the metabolic cooperation, etc. So let's consider a metaphor to explain that, a clinical analogy. So think of a tumor like a hospital unit. So with enough staff, the unit will function, no problem with that. But below a critical number in the staff, the unit is likely to collapse, even if soft staff remain. And the Ali threshold is that minimum functional staff level. That is to say, the idea is not about killing the last cancer cells, but about pushing the tumor below the size required for the collective survival. Said differently, we do not consider that any remaining cells is dangerous. We consider that below a critical tumor size, remaining cells may be unable to reestablish the disease. So Ali effect and GPC-based therapy are two different things, but clearly they can act in synergy in the context of GPC-based therapy. So let's revisit now 5 therapeutic frameworks through the lens of GPC destabilization, and let's start by the immune activation. So the immunotherapies are very interesting in that context because, as you know, certain patients that are treated with this approach often display long period of stability, followed by an abrupt and occasionally complete tumor regression, suggested that the immune system can in fact drive the GPC across a critical threshold rather than exerting a continuous cytotoxic control. Exactly like if there was a tipping point, as in other ecosystems. In that case, small immunological perturbation could potentially destabilize the entire tumor collective. The checkpoint blockade therapies exemplify this phenomenon in my view. As you know, these therapies act by releasing inhibitory signal that constrain the anti-tumor T-cell responses. These therapies are particularly efficient if the tumor is already highly infiltrated by the cytotoxic lymphocyte. And when they are reactivated at the end, their activity will result in an inversion of the local neighborhood hierarchy. And within the tumor microenvironment, this shifts the cellular dynamic from a cooperative to an antagonistic state. And clearly, this is different from simply additive killing. It represents a topological reorganization of the tumor ecosystem. From an eco-evolutionary perspective, the immune system operates as a predator guild within a co-evolving prey community, and several theoretical approaches have constantly revealed a kind of B-stability where a small increase in the immune predation and antigenicity can flip the system from a malignant attractor to extinction. Exactly like if there was a tipping point. Let's consider now the adaptive therapy designed by Bob Gatenby. He presented a very nice talk last year, if you remember. So in the context of adaptive therapy, if you're in a situation like that, with cells in green that are susceptible to the therapy and cells in black that are resistant, if you apply the maximum tolerated dose, you are going to kill all the susceptible cells, and the resistant ones will win twice. First, because they are not killed, and then because they do not have any more competitor. And this is, of course, the nightmare situation that we should absolutely avoid. So what suggests Bob Gatenby in that case? It's to apply lower quantities of therapies, and only when the tumor is growing. It's not a metronomic approach. It's only when the tumor is growing, in order to kill only a fraction of the susceptible cells to maintain a competitive equilibrium between susceptible and resistant cells. And in fact, what Bob Gatenby is doing is just playing with the GPC of the tumor to render the tumor resistant to the invasion by resistant cells. The differentiation therapy now with the ATRA treatment in the context of the acute promyelocytic leukemia. So in that case, the idea is not to kill the maximum of leukemic blasts, but to force them to differentiate into mature myeloid cells. And when the rate of differentiation is higher than 50%, the leukemia is likely to collapse just because the division produces more differentiated cells than self-renewing ones. So this is the first effect. But there is a second effect through the GPC, because as the differentiated cells exit the proliferative and cooperative network, in fact, this sooner or later alter the GPC, potentially reaching a tipping point. And it is interesting to notice in that case that no cell killing is required. Just by shifting these odds alone, it seems enough to drive the systemic failure of the malignant phenotype, a bit like in my example with the termite at the beginning of this talk. Microenvironmental normalization. So the concept of vascular normalization suggests that instead of shutting down the blood vessels, we could conversely try to change the structure of the chaotic tumor vasculature into a more functional and perfused network, because this, for instance, enhances the drug delivery. But from a GPC perspective, this approach does not act first by killing the cells, but it represents a spatial resource reconfiguration, of the malignant collective, in fact, a new ecosystem, new ecological conditions. And if you consider, for instance, the drugs that are used to inhibit the angiogenesis, usually we use these drugs with the first objective to eradicate the tumor, to starve the tumor. In the context of GPC-based therapies, this is not the objective. We could try to have lower quantity of drugs, maybe in addition with other drugs. The objective is to change the GPC of the tumor to induce a mismatch between the tumor and the microenvironment. Finally, the extension therapy and multi-strike strategy. So this approach finds its inspiration in the evolutionary dynamic of extinction. Each time it's the same story, even with the dinosaurs. We have, of course, the meteorite, the first strike, but it was not the meteorite that was able to kill all the dinosaurs in only one step. Usually the consequence of the meteorite is to strongly transform a large and genetically diversified population into a smaller one, to reduce the genetic diversity, to induce some fragmentation, and then it is often a myriad of smaller effects that would have had no effect on the large population that are going to finish the job. So in the context of dinosaurs, potentially the smaller effect could be the parasitism, the lack of food, etc. So if we transport that in a cancer context, a first strike could be, for instance, a neoadjuvant chemotherapy that is likely to reduce the size and the genetic diversity of the primary tumor, then to stop this approach, even if it works, something that we do not necessarily do all the time, and then to come with a myriad of smaller therapy that, again, would have had probably no effect on the large tumor that are going to finish the job without selecting for resistance, especially if you have some allele effect. So if we reinterpret that in the context of GPC destabilization, the first strike is likely to induce a destabilization into the tumor that could be potentially enough to obtain a durable control of the tumor without eradication. But it's possible that the tumor is able to reorganize and to restore an oncogenic GPC. So the idea is that before the tumor is able to reorganize like that, to induce a second strike to increase the level of destabilization into the tumor, hoping that this time it will be enough to obtain a durable control without eradication. But again, the tumor could potentially reorganize and come back. So the idea is, again, before the tumor is able to do that, to induce a third strike to constantly increase the level of destabilization, hoping that sooner or later we will reach some interesting tipping point or durable controls. Okay, so GPC-based therapy, but for which tumor types? Of course, if you have a small in situ carcinoma without metastasis, we do not recommend GPC-based therapy. But we think that it could be particularly relevant for tumor with a strong structural and functional complexity that limit the effectiveness of the traditional approaches that target the individual cells, typically locally advanced but non-metastatic cancer, or complex that have tumors that have complex interactions with their microenvironment, so that it's complicated to remove them completely by surgery. Of course, it could be relevant for tumors that are already resistant to cytotoxic treatments, tumor with very high level of intratumoral heterogeneity with many subpopulations of cells that are cooperating, a strong GPC. And we consider also the possibility to do that on cluster of circulating tumor cells, hoping that we could decrease their capacity to colonize other organs. So the take-home messages is that with the GPC-based therapy, the first objective is not the total eradication of the tumor cells, but to induce more or less intense destabilization into the tumor to reach some strategic tipping point, above which the tumor is likely to collapse or to shift its trajectory. There are many ways through which we can induce some destabilization into the tumors, and we need to learn more about the destabilization that are only superficial, that cannot prevent the tumor to reorganize and to relapse, from those that are able to induce some fatal, to be a fatal tipping point above which the tumor is likely to collapse, or to obtain a durable control. We need more research on that. We need maybe to understand if there are some similarities between successful destabilization, etc. And even, of course, we have nothing against new drugs. It's important to realize that we can start research on GPC-based therapy using existing drugs, depending on the quantity, the strategic order, and so on. So I hope that the money will come finally soon, and that I will have the opportunity to start this ambitious research project, and that I will have the pleasure to come back in the next years to show you the different results we obtain. And the road is for you. Mulțumesc pentru atenție.